Alright, let's look at differentiability. Alright, here's the definition. Function f is called differentiable at x equals a if the derivative at a exists. So f prime of a exists. Otherwise, f is called non-differentiable at x equals a. Right? And informally speaking, differentiability is basically smoothness. As opposed to continuity means no breakage. But differentiability requires a little bit more than continuity. The graph has to be smooth, right? So the remark would be, if it's differentiable, it is automatically continuous. Because in order to be smooth, you cannot have a breakage. So it has to be continuous at least, right? All right, there are examples of non-differentiable points. Right, first one is an obvious one. If you have a non-continuous function, then this function is not continuous at a. Then, of course, it cannot be differentiable. So this is not continuous. Right, so there's a breakage there, so it's not differentiable at a. And another one, tricky one, would be when you have a sharp corner. If you have a sharp corner, you cannot have cannot have a derivative. And the reason why that's the case is that remember that the derivative tells you about the slope of the tangent line. But if you have a sharp corner like that, we cannot really determine which line is going to represent the tangent line. So you can see that here, is that the tangent line? Or is this the tangent line? Or this is the tangent line? So we cannot identify, a single line as a tangent line. So if you have a sharp corner like that, the tangent line does not exist, which means that the slope of the tangent line cannot be determined either. Right? So when you have a sharp corner, it's not differentiable at that point x equals a. Right? Another one is, even if tangent line exists, if the tangent line turns out to be vertical, so if you have a vertical tangent line, say like that, right? So it's a vertical tangent line, right? Remember that the vertical line has undefined slope, which means that the undefined derivative, so derivative can't be there. So therefore, it's not differentiable at x equals a if you have a vertical tangent line there. All right, so let's look at a concrete example. All right, so here is a piecewise defined function f of x. F of x is 2x if x is less than 2. F of x is 6 minus x if x is greater than or equal to 2. Right? So first, let's sketch the graph and to see what the graph looks like. All right, so 2x, so y-intercept is 0, slope is 2, and so it's going to look something like that. So it's at 2, it's going to be 4. So 4 is there. And I'll probably put a dot so that I can, alright, so I have to go through there and go through the origin. So it's going to look like that. So it's going to be x is less than 2. So it's going to go like this. Alright, so this is a strict inequality, so I have to put an open circle there. And we cannot have this portion of the line because x has to be less than 2. Right? And the second formula is 6 minus x. So y-intercept is 6, so you have to go through here. Right? Then slope is negative 1. So it's going to go to the right 1 unit, go down, right down. So it's going to look like this. So here. Then we can have this line if x is greater than or equal to 2. So actually, so there's equality. I can fill the dot. Then you're gonna have a graph looks kind of like this. All right. And as you can see that this is a straight line. This portion is straight line here, so it's nice and differentiable because it's smooth. And here, nice and differentiable here. Then only problem this could have is the gap between those two pieces right here. All right. So you can see that there is a sharp corner at x equals 2. So therefore, this is a second kind of non-differentiable points. So because of the sharp corner, this function f of x is not differentiable or non-differentiable at x equals 2. So therefore, we say f is non-differentiable at x equals 2. All right. So that's it. I hope that this was clear.